Hi everyone, thank you for watching this presentation. My name is Teguh and I'll present our work on Probabilistic Iterative LQR for Short Time Horizon MPC. There are two parts in this presentation. In the first part, I will talk about our formulation of probabilistic optimal control, more specifically iterative LQR. Usually when we solve iterative LQR, the output is a single optimal solution. With the probabilistic formulation, we can obtain instead a Gaussian distribution as the output. Here we see the black line is the optimal solution that goes to the goal, while the red lines are the samples from the distributions. The distribution tells us how to move away from the optimal solution while still keeping a low cost. Now, how do you make use of this optimal distribution? Usually, the optimal trajectory is tracked by another lower level controller. And in our proposed approach, we propose to track not only the optimal solution, but the whole optimal distribution. We propose to use a short horizon MPC controller to do that. And we show that by tracking the distribution, the controller is more robust and requires less control effort, especially when encountering disturbance. This is based on minimal intervention principle. So let's move to our first part, the probabilistic optimal control. Optimal control is often used for trajectory planning of many different dynamical systems, including quadcopters in a maze-like environment, planning trajectory of centroidal motion of a humanoid robot, or even planning the whole body motion. The trajectories are often tracked by another low-level controller, and the issue is that often the optimal solution may be invisible for the subsequent controllers. And we also argue that the optimal solution does not give us much insights about the underlying task itself. So we propose to move from considering only the optimal solution to consider the whole probabilistic solution. Now let's look at the connection between quadratic function and Gaussian distribution. Here we have a quadratic function that has the minimum at x equal to 0. But this solution is not too informative for us because it doesn't tell us any other information about the underlying cost function. For example, we can have other cost functions that are quadratic and with the same solution at x equal to 0, but with different curvature. So instead of viewing x as a variable of a cost function, we can view x as a random variable that belongs to a Gaussian distribution here. This is the equation of probability density function of Gaussian. And what is the connection between the Gaussian distribution and the quadratic function? Well, if we take the negative log probability of x, we can see that the equation is basically a quadratic function. And if we compare this equation and this equation, we can see that the mean of the Gaussian is equal to x star, the solution of the minimum of the cost function, while the sigma, the covariance, is inversely proportional to the Hessian, the curvature. So we can see that the point with the highest probability of this Gaussian is equal to the minimum of the cost function, while the spread of the distribution, the covariance or the variance, is equal to the inverse of the Hessian here, or the inverse of the curvature. This means that if we have a quadratic function, we can always view it alternatively as a Gaussian distribution. And viewing it as a Gaussian distribution gives us more information because it has the covariance information, but also it allows us to do some Gaussian operations, for example, computing marginal distribution and conditional distribution, as will be seen in later slides. But how is this connected to optimal control problem? Let's look first at linear quadratic regulator and how to compute the distribution of the solution. LQR is constrained to problem with quadratic cost functions and linear dynamics. Here, xt is the state at time t, and ut is the command at time t. And one way to solve this problem is to concatenate all the xt and ut to long vectors of x and u. And then we can write the cost function more compactly as this single line. And we can also express x in terms of the initial state x0 and the whole control commands u. And if we substitute x to the equation, we can find a cost function that is a function of solely the variable u here. And if you look at the form carefully, this is our quadratic function in terms of U. So again, we can view this quadratic function as a Gaussian distribution, and we can find the solution as a Gaussian distribution where the mean is equal to the minimum of the cost function, and the covariance is equal to the inverse of the Hessian here. And since x is a linear function of U, we can compute the probability of x, which is a trajectory distribution, as a Gaussian distribution, because it's a linear function of U. So here we see that we can compute the probability distribution as a solution of LQR. That LQR is constrained to quadratic cost and linear dynamics. So we can move on to the next extension, which is iterative LQR. Iterative LQR accepts general cost and general dynamics, and it solves the problem iteratively by approximating the cost as quadratic cost and the dynamics as linear dynamics. Then we formulate an LQR problem as a function of delta x and delta u, which are the deviation from the current solution. So it does that iteratively to improve the cost function until we reach convergence. And again, since we have an LQR problem here, we can compute the probabilistic solution as a Gaussian distribution. Now note here that the mean is 0 because we are at the convergence, and at the convergence, we cannot improve the cost function anymore. So the solution is 0, but we still have the information about how to move away from this optimal solution as the covariance of the solution. Then similarly, we can compute the probability of delta x, which is a linear function of delta u, as a Gaussian distribution. And finally, we can compute the probability of x as another Gaussian distribution, where the mean is the optimal solution of the iterative LQR, while the covariance is equal to the covariance of delta x, which is found from the last LQR problem after convergence. These are some examples of optimal distributions of bicopter, inverted pendulum, and unicycle. Now, an ideal controller when tracking this distribution should be compliant in the middle when the distribution is wide, while when approaching the goal, it should be more stiff because the distribution is narrow here. We need higher precision. So how can we construct a controller that accepts distribution as the input and exhibit the desired behavior? This leads us to our second part, tracking the optimal trajectory distribution. First, let's look at the standard pipeline. Given the task, we use optimal control solver to solve the problem and find the optimal trajectory, which is then tracked by another tracking controller. In our proposed approach, we propose to use instead the probability distribution of the solution or the trajectory distribution, which is output by the long horizon iterative LQR. For the tracking controller, we use another LQR, but with shorter horizon. The shorter horizon allows us to recompute the solution at each time step in MPC fashion. So that allows us to adapt to disturbance better. While the reference distribution here allows us to consider long-term goal, even with the short horizon. Now at each time step, we need to compute the reference trajectory for the short horizon iterative LQR. And we do that by first extracting the marginal distribution from this trajectory distribution from time t to the next ts horizon. And by considering the current state of the robots, we can perform Gaussian conditioning to obtain the conditional distribution that is conditioned on xt. Then we can use this in the LQR cost function, which is divided into three parts: the tracking cost, the obstacle cost, obstacle avoidance, and the control cost. In the tracking cost, it accepts the probability distribution here and use the mean to be tracked by x, while the weight of the tracking cost is inversely proportional to the covariance of the distribution here at each time step. So when the covariance is big, that means the distribution is wide, and the weight of the cost function here is small, which means that we have a low precision tracking. While when the covariance is small, that means the distribution is narrow and the weight matrix is big, and we have high precision. So this is the behavior that we want following the minimal intervention principle. We then compare our controller against some baseline controllers. The first one is ILQR feedback controller that uses the feedback gain calculated by the long horizon ILQR. The controller is actually an instantaneous controller that tracks the next reference state using the feedback gain. However, when we move far away from the reference trajectory, the feedback gain may no longer be optimal and it can sometimes be unstable. The second controller, MPC mean, is a short horizon MPC that tracks the reference trajectory with very high cost. So you can see this as tracking a narrow reference distribution. And we see that when there is a disturbance that moves the system away from the reference trajectory, the controller will exert a very high control cost and control command that moves the system back to the reference trajectory. The third controller is MPC marginal, a short horizon MPC that tracks the marginal distribution. So it tracks the same reference trajectory as the second controller, but it uses the covariance information to know when we should be more flexible or when we should be stiff. Finally, the last controller is our proposed controller, a short horizon MPC that tracks the conditional distribution. So at each time step, we recompute the conditional distribution as the reference trajectory based on the current state of the robot. By doing that, we can exert less control effort when the precision is not required. This is how it looks like when we implement on the quadcopter with the 4 controllers. In the beginning, all of them follow the same trajectory because there is no disturbance at all. And then in the middle here, we apply a strong disturbance in the form of a vertical force that changes the velocity of the quadcopter immediately. And we see here that for our controller, it immediately finds another reference trajectory that adapts to the state of the robot. While for the other 2 controllers, they still try to stick to the mean reference trajectory, and that results in very high control cost. While here for the iterative LQR feedback, it also exerts low control cost, but we'll see that it will lead to instability. Here we see that it loses the quadcopter, while for our conditional distribution controller, it finds another trajectory that nicely converges to the task that we want, which is to achieve this goal. So in the end, if we compare the control cost of all the controllers, we see that for MPC mean and MPC marginal, the control cost is much higher than our conditional MPC. And that's the same for the maximum control command as well. We achieve the lowest control cost while still achieving the same goal position. In conclusion, we have obtained the solution of an ILQR problem as a Gaussian distribution instead of a single optimal solution. The distribution is then tracked using a short horizon MPC controller, and the proposed approach allows us to adapt more flexibly to disturbance and new situation while reducing the control cost and still achieving the primary task. This is the end of the presentation. Thank you for watching.